Example 1, find the most general antiderivative of each of the following functions. So the first one is f of x, which is equal to the sine of x. Well, first and foremost, let's just go over what is the derivative with respect to x of the cosine of x. Well, we know that that's going to give us negative sine x. Well, we want to get positive. So what we're going to have to do is we're going to go ahead and add a negative sign to that. So adding a negative sign would then make that positive. So therefore, we can say that the antiderivative of the sine of x is going to equal negative cosine of x plus the constant c. Okay, so that gives us the antiderivative of part 1. Okay, for part B, it says we want to be able to find the derivative, the antiderivative of f of x, which is equal to 1 over x. Well, let's recall that when we took the derivative of the natural log of x, that gave us 1 over x. Okay? But we also learned that the derivative with respect to x of the natural log of the absolute value of x was also equal to 1 over x. Okay? For all x where x does not equal 0. Now, Theorem 1 tells us that the general antiderivative of f of x, which is equal to 1 over x, is going to be the natural log of the absolute value of x plus c on any interval that doesn't contain 0. So, what we would say is that the antiderivative of this function is going to be the natural log of the absolute value of x plus c. Okay? So, a general antiderivative of this, okay, this is the result, but I do want to talk about the general antiderivative, okay, because of the fact that x cannot equal 0, okay, because of the fact that x cannot equal 0, then we would say that f of x is going to equal the following. You're going to have the natural log of positive x plus constant 1, provided that x is going to be greater than 0, or we have the natural log of negative x plus constant 2 if the value of x is less than 0. Okay, so therefore that just kind of proves our point, because we know that x cannot equal 0 because of the fact that that is the antiderivative that we're looking for. Okay, let's take a look at part C. It says f of x is equal to x to the power of n, where n cannot equal negative 1. Okay, so what this is, we want to use the power rule to discover an antiderivative of x to the nth power. So if we took the derivative, okay, with respect to x of the following function, we'd have x to the power of n plus 1 over n plus 1. Okay, so if we took the derivative of this function, well, that means it's going to be n plus 1 to the power to x to the power of n plus 1 minus 1, which is just going to be n, over n plus 1. Well, what happens here? Well, you can see that we can simplify those, and what we end up getting is x to the nth power. So, therefore, this tells us what the antiderivative is. So we can say that the antiderivative is going to be x to the n plus 1 over n plus 1, and don't forget we need to include the constant. So therefore there is the antiderivative of that function, and then also there's the first one. Now keep in mind here on the last one here This is valid for when n is greater than or equal to 0, since then f of x, which is equal to x to the n power, is defined on an interval. Now, if n is negative, but n does not equal -1, it is valid on any interval that doesn't contain a 0. Okay, now as we saw in example 1, every differentiation formula, when read from left to right, gives rise to an anti-differentiation formula. In this table here, table 2, we list some particular antiderivatives. Each formula in the table is true because the derivative of the function in the right column appears in the left column. In particular, the first formula says that the antiderivative of a constant times a function is the constant times the antiderivative of the function. The second formula says that the antiderivative of the sum is the sum of the antiderivatives, and we use the notation f prime, which is equal to lowercase f, capital G prime is equal to lowercase g. So here's the function, a constant times lowercase f of x, and the particular antiderivative is lowercase c times capital F of x. If we have f of x plus g of x, then the antiderivative is going to be the sum of those. X to the n, where n does not equal -1, is x to the n plus 1 over n plus 1. 1 over x, the particular antiderivative of that is the natural log of the absolute value of x. If we have the function e to the x, then the antiderivative is e to the x. The function cosine of x has an antiderivative of the sine of x. The function sine of x has an antiderivative of negative cosine of x. The function secant squared x has an antiderivative of tangent x. The function secant x times tangent x has an antiderivative of secant x. 1 over the square root of 1 minus x squared has an antiderivative of sine inverse x. And 1 over 1 plus x squared has a derivative of tangent inverse x.